Welcome to MEI Modelling with Algorithms. We're on the topic of Graphs and Networks 2, Minimum Spanning Trees and Shortest Paths, and this is video 2.1, Minimum Spanning Trees using Prim's algorithm. In this video we're going to be doing Prim's algorithm graphically. In the next video we're going to be doing it on a table. So firstly, let's say something about the type of problem that Prim's algorithm is going to solve. It's where we're trying to find what are called minimum spanning trees within graphs. Now, we've already met graphs. We've already met the type of graph that is called a tree. So that's one that contains no cycles. And the spanning tree for a graph is one that connects together all the nodes that are in that graph. So if we start, for example, with a graph that looks like this, we've got all sorts of options in terms of removing arcs until we're left with a tree. Okay, so two possibilities might be these, and what you'll notice is that yes, in both cases everything's connected and we've got no cycles, so that means we've got spanning trees. But if we add up the total weights, because this is actually a network, we have a different total here to here. So the question is, which spanning tree out of all the possibilities is going to give us the least total weight? Now, before we introduce the algorithm itself, if you want to, you could pause the video and see if you can work this out yourself. Think about what sort of thinking you would do, what steps you might do yourself if you were trying to do this. You might also want to think about the types of real-life problems that this might represent. So, for example, if you're trying to connect buildings together on a site with electricity cables, and these numbers represent the cost of connecting different buildings, then this may well be the type of problem that you end up trying to solve. And just a little bit of history there. So, Prim wasn't actually the first person to come up with this algorithm. But he did rediscover it and publish it in 1957. One thing you will notice actually in decision maths is that an awful lot of the stuff that you're learning is a lot more recently developed than the stuff in pure maths or even mechanics and statistics. It's much more of a cutting edge subject, decision mathematics. And really that's due to the advent of electronic computing. So a lot of this stuff that we're doing wouldn't actually be particularly useful without the availability of large computers on which to run these algorithms. So here is the algorithm itself. You might want to pause the video and have a little look through those steps just to make sure you understand them, and then we'll have a go at actually applying it to this network here. So the first step says that we should select any vertex. Now it may be sometimes that you're told which one to start with, it may be that you're not. It won't matter in the end. The nice thing about this algorithm is that you've got complete choice as to where you start. You will still always find the minimum spanning tree. I'm just going to take a random pick and pick node C. So I'm adding node C there. So anything that I'm adding to my tree, I'm going to draw with my red pen. Then it says select the shortest edge connected to that vertex. So I need to look at this vertex and look at all four of these edges and decide which one is the shortest. And the shortest one is this one, CL. So I'm going to add that to my tree. Now, what is really important to do when you're doing prims is to keep a track, keep note of which arcs you're adding and in which order. So I'm going to write that down now. I've added the arc CL, and it will be helpful later as well to actually write down the weight of that node next to it. The reason it's important to keep track of the order that you add the arcs in is that otherwise no one can actually tell that you did this using Prim's algorithm. There's another algorithm that you'll meet in a later video that works in a different way but would produce the same result usually. Certainly will still produce the minimum spanning tree, or it may be that you just took a guess or you did it in some other way. If someone wants to be sure that you used Prims, then you really need to be listing these arcs in the order that you find them when you do it with Prims. Right then, so then it says select the shortest edge connected to any vertex already connected. So what I need to do now is not just look at C or not just look at L, I need to look at both of them, and I need to look at all of the arcs which connect to them and decide which is the smallest. And it's this one. So that means I'm going to add node W to my tree now using arc LW, and that has a weight of 5. And then I just repeat this. So I repeat step 3 until I've got all the vertices in my tree. So now I need to look at all of these. By the way, I'm not going to be looking at this one because it doesn't take me to anything that's not already connected. So I'm looking at anything that goes from the ones which are already there to the ones which aren't. So things like this one, this one, this one, or this one. Now I've got a choice here actually. If you look at it, the two smallest ones are jointly these two. Almost always in decision maths, if you've got a situation like this where you've got two equally good choices, then it's not going to matter which one you choose. You may get a different result, but the only difference would be you'd have a different tree that was also equally minimal in terms of its total weight. So in terms of finding the minimum spanning tree, there may actually be sometimes more than one possible minimum spanning tree, and it doesn't really matter which one you find. So why don't we pick this one? So we'll add node S to our tree. So that means we're adding the arc CL, and that has a weight of 12. And then finally we need to connect R. Let's look at all the things that we can use to get to R, and the minimum one is this one with a capacity of 11. So that is RS. That has a weight of 11. And then that means that I've now connected everything. So I've finished the algorithm itself. I can see my tree there. So everything that's red there is my tree. And the only other thing I need to do is write down the total weight, which if I add these numbers up gives me 35. So just a couple of other questions to think about now in terms of Prim's algorithm. Firstly, and we did discuss this to some extent, but what would happen if we started at different vertices? You could even try it yourself. Try doing the algorithm starting at different vertex. And what happens if more than one edge can be chosen? Well, again, that actually happened when we were doing this, didn't it? And as we say, it doesn't actually matter in either of these cases. In fact, even if we end up with a different tree, it will always be the minimum. It will be equally good in terms of being a minimum tree. It'll have the same weight as any other. Okay. So here's another example, no different really from the previous one, maybe slightly larger network. What I think would be nice to do here is if you pause your video and actually have a go at doing this one by yourself, and then when you're done I'll just reveal the answer with the working. If it helps, you could take a screenshot and print it out if you want to do it that way. One thing I must remind you to do is keep track of the order of the arcs as you add them. So when you check your results against what I get, make sure that you're getting these in the same order as well. In order for us to be able to compare like with like, we're going to have to agree on the starting vertex. So even though we can pick any of them, our working is only going to look the same if we both start with the same node. So why don't we agree that we'll start with node A, and then we should find, because there aren't any arcs here which have equal weights, so we should find in this case that we get exactly the same tree, and we do it by adding arcs in exactly the same order. So pause your video now and have a go at this. So this is what you should have obtained. You've got your minimum spanning tree up there, you can see what it looks like, and importantly we've listed the arcs in the order in which Prim's algorithm added them, and the total weight for this minimum spanning tree is 174. So just before we finish, let's think about what might be some of the common errors that are made when people are using this algorithm, and then hopefully that'll help you avoid making those errors yourself. One thing is not reading the question if it tells you to start at a particular node. I can tell you in terms of exam marking, it's much easier if everyone has agreed to start on a particular node. So don't be surprised in your exams if they tell you to start at a certain node. So make sure you do that if it tells you to do that. Obviously not choosing the shortest arc to add, you do need to look carefully. One thing you do need to be careful about is that, and this actually, you'll have noticed this when doing the example just then, that you may have sometimes found that the shortest arc is say 24, and later once you add a few more nodes there might be a shorter one like an 18 or something to add. So don't get in your head that you're only ever looking for arcs longer than ones that have already been added. Do look carefully. Accidentally forming a cycle, of course, that's I mean, if you're looking at what you're doing, that you shouldn't do that, because especially with prims you're not you're really adding new nodes. So if a node's already there, then you shouldn't be adding it again. Remember to look at all the connected vertices when looking for the next edge. Again, it's just taking your time, making sure you're getting the right one. This is important as well, because as I say, if you don't record the order of the arcs, then no one can tell that you've actually used prims, which again is related to just not showing enough working. And almost always you're required to state the weight of the minimum spanning tree. So I would advise you just to get in the habit, whenever you're doing prim's algorithm, just always say what the total weight is at the end, even if it hasn't asked you to. No harm in doing that. So that concludes video 2.1, prim's algorithm done graphically. In the next video, video 2.2, we're going to see the same algorithm but done on a table.